Since we have a lot to do this week, I didn't want to introduce too much brand new material, but in this video, I do want to extend a little bit what we know about torque at individual joints and its relationship to the forces that are applied about that joint. So what we know so far is that the torque produced by a certain force is equal to the product of that force times its moment arm. Now, if you have taken or will take biomechanics or physics at IU, something you may have seen is this formula written like this with this big capital sigma in front of it, which means that if you remember from math class, this means add up, it means summation. So it means that if you want to know the total net torque acting about a joint, like the elbow joint, what you do is you add up each of the individual torques, or equivalently, you take each individual force, multiply it by its individual moment arm, and then add them up. So let me just put that summation back in, and we'll walk through an example of how to do this. And I think what I'm going to do is I'm going to have you do something like this on problem set 4 that's in a little bit more detail. I believe problem set 3 has you do a little bit of this, but it's not the focus of the assignment. So let's, to our skeleton here, let's add a dumbbell in his hands. And let's start to think about the case of a dumbbell curl exercise where we're trying to produce enough torque to flex the elbow. Now, I know for the time being, I know in this picture I have the triceps pictured, but we are going to assume that you have a pretty good ability to isolate just your biceps and not have any co-contraction here. So let's consider the forces produced by, and let me see if I can find a color that will show up well. The force produced by this bicep muscle, this bicep muscle, and then there's two more forces that we need to consider. One of them should be obvious. One of them is the weight force from the dumbbell, like this. So let me draw this nice and big because maybe it's a heavy dumbbell. Big, strong weight force vector. So if this is a 50-pound dumbbell, this would be a 50-pound force, which would be, what would that be? Maybe 220 newtons. Maybe I'll just put that out there, 220 newtons, like this. There's one more force though, and the force is from the weight of the arm. So we didn't really talk about this in the last unit, but imagine you were like you'd been in a cast for a long time and your muscles were really weak. Your physical therapist might have you do bicep curls with no weight at all. And if your muscles were really atrophied, you might find that difficult. And the reason is because we can consider your arm as being kind of like a stick with a weight in the middle. That weight would be at the center of mass if you're familiar with that concept. But if you're not, don't worry about it. So the weight of your arm, it's only a few pounds, but if you have really weak muscles, that's something. That's some amount of weight that you have to work against. So just to make the math easy, let's say it's I don't know, 5 newtons, be slightly more than a pound. So this would be, the interpretation is that's the weight of all of this stuff, bone, muscle, skin, tendons, ligaments in your forearm and in your wrist and your hand. So let's label, maybe I'll just call this, these would be the brachioradialis and the brachialis, but maybe I'll just call it FB1 for the first bicep muscle here, and we'll just call this FB2, the force of the second bicep muscle. Now, to consider what's going to happen in this scenario, or to consider how much force each of these muscles needs to produce in order to produce a torque that's greater than or a torque that's going to flex the elbow as opposed to extend it. We need to know the moment arms. So let me draw them first of all. Here's the moment arm for this force. Maybe I'll call it R arm. And then I could draw, and maybe should draw, the moment arm for the weight, the dumbbell like this. But to give myself some more room, hopefully you're okay with me taking this, and I'm just going to drop it down to here and draw it like a bracket. So it's just this horizontal distance. R dB for dumbbell. So for this force and for this force, I can immediately calculate how much torque they're going to produce. So each of them, the torque from the arm is going to be equal to 5 times that R arm. And then let's put some numbers on that. Let's just say, this, what does that look like? Maybe 0.2 meters. Like you could literally measure this with a ruler if you wanted to. And maybe this one is 0.4 meters. So the torque of the arm, the torque generated by the weight of the arm is going to be 5, this, multiplied by 0.2. So what is that going to be? That's going to be 1. It's going to be 1 unit is Newton meter of torque. And let's look at this and think about what direction that's going to make the elbow go. I think it's going to be a elbow extension torque. I mean, you can imagine, right, like the limiting case of the arm or the dumbbell is really heavy and your muscles aren't activated at all. Clearly, that's going to extend your elbow. Now, you can get fancy with defining, say, positive being like this and just saying this is going to be negative for that reason. Let's specifically say extension torque. 1 Newton meter of extension torque. And we can do the same thing with the torque created by the dumbbell. It's going to be the weight of the dumbbell, or its force, 220, times 0.4. Which, let me use a calculator to make sure I do this correctly. It's going to be 88 Newton meters. And again, we'll write down 88 Newton meters. Again, this is going to be an elbow extension torque. You might be wondering, how do I know this? There's 2 ways to think about it. One of them is just eyeballing it and using your intuitions. Like I think mechanically you understand that this force is going to have the tendency to extend the elbow joint as opposed to flex it. Another way of thinking about it is the moment arm, what is its orientation relative to the elbow joint? So is it going off in this way or is it going off this way? But I think for most of the things, or virtually everything you'll encounter in this class, you will have good intuitions on what the result of the force will be. And that's also the case for the muscles here. So this force and this force quite clearly are going to be creating elbow flexion torques. So let's put some numbers down for the moment arms, which, by the way, I would draw as this FB1 down here. I would say the moment arm is about that big. It's about that distance. And then FB2, it's probably that distance. So already you can see FB2 has a bigger moment arm. Maybe it's, again, I'm just making up numbers here, but let's suppose it's 0.01, so 1 centimeter for this one, and then 0.02. Put R for moment arm here. Now, let's think about what is going to happen in this problem. If the forces from the muscles are 0, then you get 1 Newton meter of elbow extension torque and 1 and 88 newton meters of elbow extension torque from respectively the arm and the dumbbell. So we could write that out. We could say the sum of the torques in this case is going to be no torque at all from here and here if those muscles aren't activated. 88 plus 1, so 89 newton meters of elbow extension torque. So this gives us intuitions on what the role of the bicep muscles is during a bicep curl. Their job is to produce, if you're doing this concentrically, if you're trying to go up, their job is to produce at least 89 newton meters of total torque or more, right? So solving this is actually not trivial. Generally what I will do, and we'll explore this in a problem set, generally what I will do for at least the next week is I will tell you what the forces are, and then you can calculate what the net result is. So let's say this is, I'll write it out in a corresponding color, I don't know, 1,000 newtons here. Well, no, that seems a little high. Let's say this is 500 newtons here, and this is 200 newtons here. So this muscle is contracting with 500 newtons of force. This muscle is contracting with 200 newtons of force. How much torque are they producing? Well, it's going to be 500 times the moment arm of 0.02 plus 200 times the moment arm of 0.01. So let's do some math. I think that's going to be, 500 times 0.02, 10, and then, 2? So this is 10 newton meters of, let's say, flexion torque. And this one is 2 newton meters of flexion torque. How do I know that? It's because I know that the bicep muscles create elbow flexion torques. And then we would add these up. So if I have 10 plus 2, I get 12 newton meters. So 12 newton meters of flexion torque. But we had 89 newton meters of extension torque, which means that in this case, these muscle contractions are not strong enough. So we're going to get a total elbow torque that is an extensor. So we could say maybe one way of writing this out is we could have like 12 on this side of the equation, and then or maybe we could just define extension as positive and flexion as negative, and then we would just do 89 minus 12, and we would still get a positive number of 77, which means the net effect of all of this, of this force and this force and this force and this force, would be 77 newton meters of extension torque, which would mean that this would be, if we kind of played, this is like frozen in time, but if we played this forward, we would see the elbow extending, and this would be an eccentric muscle contraction, right? Because these muscles are not producing enough force to overcome the torque generated by the weight of the dumbbell and the weight of the arm. And if you inspect the individual torques and moment arms, you can see that the big culprit here is this big force multiplied by this large moment arm. So to offset it, we would need to dramatically increase these muscle forces. And this can give you some intuitions as to why muscle forces in the body tend to be quite large. It's because muscles have very small moment arms compared to the moment arms you might get from, say, a weight like this. So I wanted to introduce this worked example of how to add up the torque contributions of different components of a system, and by a system I just mean for a given problem, a given exercise. You've got some weight from the arm like this. You've got some weight from a dumbbell in your hand like this. You've got this muscle and this muscle producing flexor, elbow flexor torques to try to overcome the elbow extension torques. And in the next few weeks, we will explore how the body navigates this dynamic of how do I choose the muscle forces that overcome or accomplish the task that I want to accomplish.